Cool. Welcome to lecture 6. And today we're going to still be talking about state estimation, but specifically we're going to focus in on instantiating it for the Musher car, right? And so just to recap, we talked about the Bayesian filter, and the Bayesian filter starts from a belief at time set 0, pushes things forward through a motion model, right? So the motion model is your dynamics model, xt given u txt minus 1. You multiply it by the previous belief, sum of over all xt minus 1. That's how you do prediction. And then you correction by taking a measurement, weighting every belief xt by the likelihood that it produced that measurement, p of zt given xt, and then renormalize. Okay? And so what we're going to think about today is that there's like these two entities we care about, the motion model, p of xt given u xt minus 1, and the measurement model, which is p of zt given xt. And we're going to essentially try and instantiate both of these, right? So we're going to try and instantiate both of these for the Musher car and the LiDAR sensor. Okay, so in the context of the car, the prediction model is going to say, if I was at some position, I applied some speed and some steering angle, like what is the likelihood that, what is the likelihood of the next state? And what is the correction model? It's saying that if I was at some position and I kind of knew the map of the world, what is the likelihood I got some set of LiDAR readings? And so we're going to try and basically work out the form of the prediction model and the correction model. Okay, so the prediction model is just kind of, it's essentially some small changes on top of physics, but we're just going to do some physics, some trigonometry, and we're going to try and figure out what the position of the car is going to be. Depending on your current position and some actions, which are speed and steering. And so we talked about this briefly last time, but the state of the car is going to be your x coordinate, your y coordinate, and your heading. Right? So the heading is what your angle is. And your actions are going to be your speed and your steering angle, right? So the speed is like what speed you apply to the rear wheels, and the steering angle is what angle you apply to the front wheels, right? So it's a front wheel steering, rear wheel drive. And so we're going to use those as the actions and those as the state. And what we're going to try and do is determine x dot, right? Where x dot being dx over dt. So we're going to try and determine, so there we go. We're going to try and determine dx over dt, like, which is in continuous time, right? And once you have it in continuous time, you're going to try and integrate it over a small time window to give you the next x, y, and theta. Right? And so we're going to try and figure out dx dt, where x is x, y, and theta. Then we're going to integrate that dx dt over a small period of time in order to give us the next x, right? Okay. And the second thing we're going to do is we're going to say that our motion model in the first step is going to be perfect. But we know that all motion models are not perfect. And so we're going to add some noise and stochasticity to the problem. So we're going to have a probability distribution over the next state, not just, a single perfect next state. Right? So those are going to be our two steps in the motion model. Yeah? Everyone with me? Okay. So the key concept we're going to use for the motion model is this idea of the instantaneous center of rotation. So whenever you think of a car, right, a car is going to not just like rotate in place. A car is going to have forward velocity and it's going to have steering angle. So a car is going to kind of move like this, right? Okay, if you all drive, the cars don't like move sideways, right? So that's why it's non-holonomic. Holonomic would be able to move sideways, and cars here would be non-holonomic. So in some sense, you can think of this as like it's translating, but it's also rotating, right? And so whenever you have something that is both translating and rotating, you can say that you can cast it as a pure rotation around some point, right? So imagine there was some point outside of the body of the car, and relative to that point, it is pure rotation, right? So you can kind of think of it as like, let's erase this for a second. Let's say your car was moving like this, right? You can say that like there's essentially a point here relative to which you can think of this as like, I think I mentioned this last time, but if you have like a disk This is like a pure rotation around this point. But if you think of the car sitting on a disk, it's like a pure rotation around some point, and that point is going to be the instantaneous center of rotation. And the reason you want to do reason you want to compute something where it's a pure rotation is because you like know lots of properties about rotation. Like things are like perpendicular to rotation, there's like tangents you can compute, and like trigonometry becomes a lot easier. Right? So what we're going to do is we're going to try and find that instantaneous center of rotation and use it to compute our motion model. Yeah. Okay. So that's a recap of what we did last time. We're gonna complete up the rest of motion models. We'll try and talk about some observation models for the LiDAR, and then we'll start talking about particle filters. Okay, so this is what our car is going to look like, right? So at a particular state, you are like at any particular time, you're at XY, which is your position. Theta is going to be your angle from the x-axis, right? So this is your current, this is what you call your heading, right? Delta is going to be your steering angle. Like what is your steering angle off of your current heading, right? And the velocity is going to be what is the velocity you apply to the rear wheels, right? Okay. So what we need to compute is dx over dt. We need to compute dy over dt, and we compute d theta over dt. Yeah. Okay. So walk me through it. What's dx over dt gonna look like? Your velocity is along the body of the car, right? So your velocity, like your car's moving with velocity v in this direction. So along the x-axis, what is the component of velocity going to be? It's v along the body of the car. So what is it going to be along the x-axis? We know that maybe one thing that will help is we know that this angle here is theta. Your thought? Yeah. V cosine theta, yeah. And what about dy dt? D sine theta, right? And so you can kind of think of it as like this is v along the hypotenuse, and to like you project it on the x and y axis, right? So just v cosine theta and v sine theta. So it's v cosine theta, v sine theta. And the theta dot is a little more annoying, right? You're trying to figure out what is the change in heading. And the way you're going to do that is you're going to think about the instantaneous center of rotation. So there's going to be an instantaneous center of rotation, and you can kind of think of it as like when you have the instantaneous center of rotation, like you can think of it as a circle that passes through like this point and this point, right? And you know that the radius of a circle is perpendicular to the tangent, right? And so you know that like this thing is 90 degrees, and you know that this thing is going to be 90 degrees, right? So we're saying that the car wheels don't have any slip, right? So it's going to say that like this thing is going to move like this. The back wheels are going to move like this, and the front wheels are going to move like this. Right? And so essentially relative to the instantaneous center of rotation, the nice thing that you can write is that you can write like this angle is 90 degrees, this angle is 90 degrees, and so we can compute some more angles, which are nice, right? So if this is delta, this is 90, then this becomes 90 minus delta, right? And now this is 90, this is 90 minus delta, so this angle becomes delta, right? It's like angle math, right? You're just saying like this is delta, this is 90, this is 90 minus delta, because the lines have to sum up to 180. The angles in a line have to sum up to 180. And the angles in a triangle have to sum up to 180. So 90, 90 minus delta, delta. Right? So the nice thing that you can do then is you can say that theta dot, right? You're trying to find the change in heading. Theta dot is equal to like the angular velocity, right? Like if you think about the rotation around the center of instantaneous center of rotation is equal to the angular velocity, and we know that the angular velocity is equal to the like linear velocity divided by the radius, right? And so if it's equal to the linear velocity divided by the radius, the problem is we don't know this radius, right? Like we don't know what the radius is. We need to just compute the radius in terms of known quantities. Like the quantities we know are x, y, theta, v, delta, and we know how long the car is, right? So we know v, delta, and L, but we do not know R. So we know that angular velocity omega is the linear velocity v divided by the radius R, but we don't know the radius, right? And so the way you're going to compute the radius is you're going to look at this triangle. You're going to look at, maybe let me just draw it here. You're going to look at like this triangle, right? It had 90 minus delta, right? And so what that tells you is you can compute the tangent delta, right? So if you look at tangent delta, it's equal to L over R, just trigonometry, right? So if I know that tangent delta is L over R, then R is just L over tangent delta, right? So you can just say that like my radius R is equal to L over tangent delta, right? And now I just stick this guy in to here. That's it. And so I get V over L divided by tangent delta. Tangent delta goes to the numerator, so I get V tangent delta divided by L. Yeah. So x dot is V cosine theta, y dot is V sine theta, and theta dot is V tangent delta divided by L. And this kind of makes sense, right? Like your your x velocity depends on your heading, your y velocity depends on your heading, and your change in angle depends on your steering angle, right? But if you want to like look through this again, like the way to compute this is you just try to look at these like the important thing is because it's a pure rotation, like this thing is going to be perpendicular and this thing is going to be perpendicular, right? And if there was slip, this wouldn't hold. Like slip means the car is moving sideways. But because there's no slip, this doesn't move sideways, and this doesn't slip, and this doesn't slip. So this has to be perpendicular, this has to be perpendicular. And that allows you to compute that this angle is delta, which means that tangent delta is L over R, which allows you to compute theta dot, right? So just to recap, x dot is V cosine theta, y dot is V sine theta, theta dot is V over R, and R is L over tangent delta, right? And the facts that we used were just projection of velocity along the axes, and then the fact that it's a rotation, so you can compute like the tangents. Okay, so if we write this out cleanly, right, you essentially have theta dot, x dot, and y dot. And all you're going to do is integrate that to come up with your next x, next y, and next theta, right? So we're going to do some simple integration. It's going to give us our next x, next y, and next theta. And then we're going to add some noise. Right? So the identities we know are x dot is V cosine theta, y dot is V sine theta, theta dot is V tangent delta over L. Right? So let's start with x dot. So what we're going to do is we're going to take x dot, we're going to integrate it over some small period of time, right? And so we're going to say V cosine theta integrated over an interval from t to t prime, right? So what is the integral of V cosine theta? Yeah, V sine theta, right? The integral of V cosine theta is just going to be V sine theta, right? But like one thing that you have to be careful about here is that the integral here is with respect to like t, right? And your cosine theta is a function of theta, right? And so what you're going to do is you're going to multiply and divide by theta dot, like d theta over dt, right? And then you're going to say that like we're going to assume that theta dot, the rate of change of theta dot, or the rate of change of theta is going to remain constant in that interval. Like you can't just, if it is like the problem is the integration variable here and this thing are not the same, right? Like this is in theta, this is in t, right? And so what you're going to do is you're going to multiply and divide by d theta over dt, right? And then you're going to say that theta dot is going to be consistent over this interval. We're not saying that theta is going to be consistent. Theta dot is going to be consistent, which means that the rate of change of theta will be consistent over your interval. And so the steps are you're going to take this integral, right? You're going to say that like, okay, my integral variable and the function are not in the same variable right now. So I'm going to multiply and divide by d theta over dt, right? And then I'm going to say that theta dot is going to be constant. So I can take out this thing from the integral because they're constant. And I can cancel the dt's. So then I have v over theta dot times the integral from theta to theta prime of cosine theta. And now you can see the variable that is being integrated and the function they're in the same variable, right? So you can integrate it to sine theta, like you were just saying. And so you can write this as v over theta dot times sine theta prime minus sine theta, right? So the important thing here is we took one extra step. You can't just integrate. You can't just integrate this first thing here because it's not like theta is not, we don't know, like it's cosine theta, which is itself a function of t, right? And so instead what you did is you multiplied and divided by d theta over dt. You canceled out the dt's and now you integrate in terms of theta, not in terms. Okay, so essentially what that's going to give you is v over theta dot times sine theta prime minus sine theta. You know from your identities that theta dot is v tangent delta over L. So if you substitute, it's going to be v over theta dot sine theta prime minus sine theta. Theta dot is v tangent delta over L. So it's going to be v over v tangent delta times L. The v's cancel times sine theta prime minus sine theta. Right? So this is what your change in x is going to be. L over tangent delta times sine theta prime minus sine theta. Okay. It's a little bit confusing, but let's maybe do a quick recap again. We started by integrating v cosine theta. Theta itself is a function of t, right? So you have to convert this integral into an integral over theta. You have to multiply and divide by theta dot. V and theta dot are going to be constant over this interval. They come out. Integral cosine theta is sine theta. And then you substitute in the value for theta dot from our identities and the like. Yeah. And so this is going to be our expression for delta x. We're going to do something similar for delta y. Like the only difference is we're going to integrate v sine theta, right? And if you integrate v sine theta, you're going to do the same thing. You're going to multiply and divide by theta dot. These things will cancel, but the only thing is you're integrating sine theta now. And the integral of sine theta is what? Negative cosine, right? So if you're going to work out almost exactly the same math, it's just going to be sine flipped, and it's going to be cosine, right? So delta x is L over tangent delta sine theta prime minus sine theta. Delta y is L over tangent delta cosine theta minus cosine theta prime. But in both of these expressions, I don't know what theta prime is going to be, right? So I have to integrate theta also. So if I want to compute delta theta, I'm just going to integrate theta dot dt. But as we just talked about, theta dot is, we're going to say that the steering angle is, or the rate of change of the steering angle is, or rate of change of the heading is going to be consistent over that integral, right? So we're going to say that theta dot is going to be consistent over my integral. So I'm going to take this out, right? And if I'm going to take this out, then I just have theta dot times integral t to t prime of dt, right? Which is just theta dot delta t. And theta dot is v tangent delta over L. So your delta theta just becomes v tangent delta over L times delta t. That's it, right? So you choose your like period of integration, which is delta t. You can compute delta theta by integrating theta dot. It's the easiest one, right? And then you can use that in order to compute delta x and delta y. Questions? looking a little confused. What's up? Questions?
Oh, why see the dot is
Why is theta dot constant? Because you're saying that like you're going to be integrating for a small period of time. And in that small period of time, my steering angle will be constant. For the next period of time, my steering angle will change, right? But I'm saying my rate of change of the angle will be the same. My angle may change, but my rate of change will be the same. It's like if that assumption is going to be false if my period of integration was longer, but I'm going to have a small period of integration. So it's almost like I'm going to do this like very frequently. And so it's arguing that like essentially between now and like 0.1 seconds from now, I'm not going to change my steering angle a lot. Okay, so the heading is going to change, which means that theta dot is not zero, but theta dot is constant for that. Okay, so let's put together all the stuff that we have. Right, so we computed delta theta. Delta theta is going to be V tangent delta over L times delta T, right? So V tangent delta over L times delta T, that's going to be your delta theta. Delta theta is going to give me a way to go from theta T minus 1 to theta T, right? First step. Now that I know theta T, I can compute delta X. So delta X, as we saw earlier, was L over tangent delta sine theta prime minus sine theta. We computed theta prime. We knew theta from before, right? So you can compute delta X. And so you can say that XT is equal to the previous XT minus 1 plus L over tangent delta sine theta T minus sine theta T minus 1, right? Just substituting from the previous step. And in the last step, you're going to do the same thing for delta Y, right? You're going to say delta Y is L over tangent delta cosine theta minus cosine theta prime. We computed theta prime in the first step. You're just going to substitute this guy into here, this guy into here. And so you have the next X, the next Y, and the next theta. Yeah. Okay. So just to recap what we did in the motion model, right? We started by doing some trigonometry. The trigonometry gave us X dot, Y dot, and theta dot. Right? The important thing is we compute the instantaneous center of rotation. That gave us some angles here. And we were able to compute X dot, Y dot, and theta dot in terms of all known entities. And when I say known entities, I mean like X, Y, theta, V, delta, and the length of the car. Like nothing privileged, like all things you know right now, right? All things that are either part of the state or part of the action or part of the like specification of the car. Then we just integrated those terms. The only thing to remember here is that you want your function and your integral to be in the same variable, right? So you just did essentially the chain rule, right? So you just multiplied and divided by theta dot. You did the chain rule. The only assumption here is that theta dot does not change in your interval. That gives you delta x, delta y, and delta theta. And then you just computed delta x, delta y, delta theta to give you the next state, right? You said like theta t is equal to theta t minus 1 plus delta theta. Same for x, same for y. Yeah. So in your homework, you're just going to literally implement this. It's this plus a bit of extra like features, but in some ways it's exactly this. So the steps in our motion model are going to be we computed x dot, we then integrated x dot to get the next x, y, and theta. Now finally we have to add some noise, right? So if I wanted to add some noise, how would you guys add noise to this model? I integrated x, y, theta, it gave me a deterministic function. The deterministic function went from xt and ut to xt plus 1, right? We computed a single function that goes from xt and ut to some xt plus 1, but I need to be probabilistic around the next step, right? So how would I do that? It actually went from ut xt minus 1 to xt. How would I add noise to this function? Intuitively, how might I do it? What do you think?
Like fairly random value to formulas. Like if
Yeah.
you just use compound.
Right. So, yeah. So I think you want to be careful about what you're making random, right? So specifically what we're going to do is we're going to add two sources of noise, input noise and output noise. So the first thing we're going to do is we're going to say, maybe the actions we took weren't exactly the actions that were executed, right? So there's some noise in like your actuator logic, right? So we're going to add a little bit of noise to this. Right? And then we're going to say like, maybe your function was a little wrong, right? And so we're going to say, we're going to add a little bit of noise to this, right? So the way you're going to make your function noisy is you're going to have some input noise, which changes ut to ut plus epsilon, where epsilon is sampled from some Gaussian. And the way you're going to make the output noisy is you're going to add again a separate Gaussian, which is sampled from a Gaussian with a separate covariance. But this kind of represents noise in the actions. This kind of represents noise in the states, right? And so the probabilistic nature of the next state is going to depend both on noise in the like model and in noise in the action. And so your homework, you're going to implement something where you add noise to both the input in terms of the actions and the output in terms of the states. Like the rule of thumb in terms of adding stochasticity is you want to capture uncertainty wherever there could be error, right? So it could be that you executed the wrong action. It could be that your model was wrong. You want to account for both of those sources of error. Cool. So that's our motion model. There's a bunch of reasons why that motion model is probabilistic. We've talked about this a couple of times before, but basically it's arguing that your model is too simplistic or you're missing some factors, right? And you add stochasticity for that. And so as we just talked about, we're going to add noise to the control before sending it into this integration. We're going to add noise to the output of the integration. And it's going to capture the idea that like our controls were wrong or our model was wrong. So kind of thought about graphically. If you think of your car time step here, this is what your integration would give you. And then you kind of add some noise around it, right? So like if you think of it in terms of particles, this is where you think your car is right now. The next step, you might think your car is like in one of these positions. So if you like 100% knew that your car was here, at the next time step, there's going to be additional uncertainty about where your car will be in like some range around this this integral, right? So the important thing is we computed the integral assuming no noise. Then you added noise to the input, you added noise to the output. Okay, any questions? Does it make sense overall? Motion model seems reasonable. So this seems like a toy model, but it's like used in lots and lots and lots of places. It's called the kinematic bicycle model because you can see that you kind of reduced this four-wheeled car to almost like a bicycle, right? You said that I'm just going to worry about the main axis here. It's like a two-wheel thing. The back wheel goes straight, the front wheel can turn, right? The difference between a four-wheel thing and a two-wheel thing is like the ability to have slip this way, right? And like the wheels can move at different velocities. Because not everything is perfectly rigid. And you're not like in reality, you're not going to be perfectly not slipping. And the wheels are not going to all move at the same speed. So the kinematic bicycle model is a simplification of the four-wheel, right? And so a lot of the like extra research in the space is like better models of four-wheel vehicles. Okay. So that concludes what we're going to talk about with motion models, right? So that's the model of our car. And now we just need to get the model of our sensor, and then we can implement a Bayesian filter. Right? Okay, so let's keep going to the model of our observations, right? So the thing we're going to think about is specifically in the context of LiDAR. So LiDAR is a particular type of sensor where you're shooting light beams out, and then you're seeing the time that it takes for the light beams to come back to you, right? So if you've seen like Waymos, they're like rotating super fast on top, and they're shooting light beams out in all directions, right? And then you're measuring like how much time does the light beam take to come back to you for each separate light beam that you shot out, right? So you can kind of think of it as like you shoot out light beams in a bunch of different directions, and then you measure time of flight. So you measure like how much time it takes to come back in each of those directions, and that gives you a reading of the depth in each of those directions, like how far is an obstacle in each of those directions, right? So why should we use LiDAR? Like, why is LiDAR good? Thoughts? What do you think? Yeah, exactly. And so if you had to use something like a camera, cameras are great, but like you have to like understand the semantic information in the scene. You don't always understand depth. And so especially when you're dealing with spatial things, like LiDAR is particularly meaningful because it like gives you distance to an obstacle, which is really what you care about when avoiding obstacles, right? And so LiDAR is used in cars, in helicopters, in planes, like and it's generally a pretty fast way of making measurements. But we're going to like try and model a LiDAR and see what the pitfalls are. But in general, we're going to think about a LiDAR model as not being perfectly accurate. And we're going to try and model what the causes of the inaccuracy are. Right? And so some causes of inaccuracy for a LiDAR model are that your map was a little bit wrong. There was an unexpected person that showed up, right? One thing with light is if you have like something absorbing, it doesn't come back. That doesn't mean there's no obstacle. That means that your light didn't come back. And then there's things like, are your beams coming back? Like if you have something that is like a scattering surface and your light beam shoots this way and it comes back that way, like it doesn't come back in a straight line like you'd like, right? And so you need to be able to have your LiDAR model account for all of those things. Because your readings in an idealized world, right? Like if I drew something where it's like, here's my car, here's my LiDAR, and if there's an obstacle here and it's gonna shoot back perfectly, will be violated if the surface is absorbing, if the surface is scattering, if there's like some unexpected person that shows up over here, right? Like all of those things will change the measurements. And so if your sensor model doesn't account for them, you will like think there's an obstacle where there's none, right? And so we have to make sure that our sensor model accounts for all these possible misspecifications. Okay. So what we really want to do with the Bayesian filter is we want to make sure that we're not overconfident, right? So if you're overconfident, it's catastrophic because you're going to think that like there's an obstacle where there's none, or there's no obstacle where there is one, and you're going to take an action that could be catastrophic, right? And so we're going to think about some specific modes of failure to avoid overconfidence in a Bayesian filter with LiDAR. And so the first thing we're going to do is that we're going to notice that a LiDAR scan is like a lot of different beams, right? So it's not just one reading. A LiDAR scan is more like an array or a vector, right? So it's like if my LiDAR is going to shoot in like all of these directions, and I'm going to have like k different values each for each of these beams, right? And you can kind of think of like each of like a z as a set of those values, right? So the first thing we're going to do is we're going to assume conditional independence between those beams. Right? So I'm going to say, I'm going to shoot out a bunch of beams. The beams are going to come back. And then I'm going to assume that like each of those beams are conditionally independent, which means that the likelihood of this thing giving me a measurement will be independent from the likelihood of this thing giving me a measurement will be independent from the likelihood of this thing giving me a measurement. Right? And so why do I want to do that? Well, it's because you can separate out when you have something that is conditionally independent, right? If you remember, if you have P of A, comma B given C, and you know that A and B are conditionally independent given C, you can write this as P of A given C and P of B given C, right? So the nice part about assuming conditional independence is that I don't have to build a model of like 10 LiDAR beams at once and how they behave. I can build a model for one LiDAR beam and just multiply it 10 times, right? And so the important thing is that when you assume conditional independence, you've reduced the modeling to a single LiDAR beam. So that's why it's often called the single LiDAR beam model, because you're modeling how a single LiDAR beam behaves and then multiplying it for your 30 LiDAR beams or whatever, your K LiDAR beams that are shooting out. Right? But it's an assumption. It's an assumption of conditional independence. Okay. So important thing is like you can kind of think of like The sensor measurement at any time is ZT, but ZT in a LiDAR comprises of like 100 beams, 30 beams, 50 beams, whatever. And we're going to assume that all the beams are independent. When is that bad? Like when is it bad to assume the beams are independent? Or when does it not hold? Thoughts? So remember, conditional independence means that like if I knew Z2, it would not change the probability distribution of Z1, right? They're conditionally independent, conditioned on like the map, right? And your state. So what's the scenario where two things are not conditionally independent for LiDAR beams? Good. Obstacle is moving. Although like the obstacle is moving doesn't necessarily, it depends how the obstacle is moving. And if you know that, but if you didn't know how the obstacle is moving, the probabilities are still independent. So one way of thinking about where this is related, if you have two LiDAR beams that are really close to each other. Let's imagine you have two LiDAR beams that are like 3 degrees apart. Now, if this one is, if there and obstacles are like, let's say like not atoms, but they're like at least this big. Like if two LiDAR beams are really close to each other, then if this one is going to be positive, then this one, if this one's going to detect an obstacle, then probably this one is also going to detect an obstacle, right? So they're like super correlated. Because like the fact that this one showed me an obstacle, the fact that this beam showed me an obstacle probably suggests that this beam will also show me an obstacle because they're super close together, right? And so the reason that's bad is because when you multiply these likelihoods, you're going to like become overconfident quickly because you're saying like you're double counting, right? If you remember how we did conditional independence, you treat two things that are not conditionally independent as conditionally independent, you're just going to keep like increasing likelihood falsely, right? And so the important thing is that in LiDAR beams, if LiDAR beams are too close together, you'll have overconfidence. And so you like falsely think that there's an obstacle, even if there's not. Right? And so the important thing is try to space out your LiDAR beams. Right? Don't just shoot like LiDAR beams 1 degree apart. Okay. So in the single beam sensor model, right, our measurement is going to be a distance. We're going to measure time of flight. We're going to like take speed of light and time, and we're going to compute distance, right? And so our measurement ZT is going to be a distance, and we're going to try and build a model of what the distance is going to be, conditioned on XT, which is your state of the world, and the map, right? And so the important thing we're going to do is we're going to like think of the different sources of failure, and that's going to give us a probabilistic model. So this is my car. I'm going to shoot my LiDAR, let's say in this direction. This is like the true distance. And let's call it like maybe ZTK star. And I want to build a probabilistic model of what the actual reading that I get from a LiDAR could be dependent on the like true distance, right? Okay, so what are some sources of failure that you might have in a LiDAR? I covered some of them already, but what are some sources of failure?
Rain.
Rain, yeah. Rain or like weather conditions. Other thoughts? Unexpected obstacles, right? We just talked about unexpected obstacles. Like if you didn't account for obstacles in your map, suddenly there was someone, right? Um, other factors we didn't consider.
I'm not sure, but if the like obstacle reflects either the other direction.
So obstacle moves or something like that? Stairs, you said? Okay. got it. Got it. Oh, you're saying like it kind of bounces off the stairs and goes somewhere else. Could have like absorbing material, right? You could have just like sensor failure, like this LiDAR just conks out every once in a while, right? And so we're specifically going to model four different sources, right? We're going to think about some like measurement noise in any electronic sensor. We're going to think about unexpected objects. We're going to think about complete sensor failures, and we're going to think about some degree of just like random measurements. And so the first type of failure we're going to think about is just local measurement noise. Like every electronic measurement device has a little bit of error, right? And so usually you can model that with a Gaussian. So let's say ZTK star was your true distance. You can model that with a Gaussian around ZTK star, right? So that's going to be our first factor, which is local measurement noise. The difficult thing to figure out here is like what should be the variance of that, and that depends on like the particular sensor you have, right? Basically, it says that like if that distance was truly 10 meters, like your sensor might return 10.1, right? And so you want to like account for some noise in like the accuracy of your sensor. Um, so it's like a pretty simple Gaussian noise, which is just centered around the true distance, right? So like ZTK star is your true distance. The likelihood of producing on the x-axis is different Z you can produce, right? So the likelihood of producing ZTK star is the highest. That's the most accurate, but there's some likelihood of making some small error. And so just in Gaussian noise around the true distance. That's the first type of error we'll have. Right. The second type of error we're going to think about is that of unexpected objects. So it's basically saying like you have a map of the world, right? And then suddenly someone comes in front of the map, or like there's something that passes by, there's a cat, something else that is unexpected. And so like the question is like, what is the likelihood of getting these kind of values that are shorter than the true distance because of unexpected objects, right? And the math here is not super important, but it's more important to get the intuition, right? It's basically saying that the likelihood of like if there was an unexpected object in the scene, if the first thing you want to notice is that if the unexpected object was further than the true object, the likelihood is basically zero, right? It's like if it's like imagine this was the obstacle, and the unexpected object was here, and the LiDAR was shooting from here, like it's going to hit our obstacle first. It's not going to hit the unexpected object because it's after, right? And so you don't need to worry about any distance that is further than the true distance because it's going to hit the true obstacle first, right? And so you're saying that I don't care about anything that's further. Now, if you think about things that are shorter, right, it's basically saying like the LiDAR was here, the obstacle was here, and imagine there was unexpected objects in between, right? And what this probability is saying is that the likelihood of getting a shorter reading is higher than the likelihood of getting like a further reading. So it's like it's saying that when I have an obstacle, I will like more likely get 1 meter than I will get 5 meters, right? And so this is what you call a Poisson distribution, right? But you can kind of think of it as just like a decreasing distribution where your likelihood of getting short values is higher than the likelihood of getting longer values. And the intuition here is quite simple. It's basically saying that like, in order for me to get this value, I just like imagine that the obstacles appeared with uniform likelihood between here. Like the obstacles are appearing like with uniform probability anywhere, right? But in order to get a sensor reading of 1, I just need to have an obstacle here. But if I need to get a sensor reading of 2, I need to have no obstacle here and an obstacle here. And if I have to get a sensor reading of 3, I have to have no obstacle here, no obstacle here, and obstacle here. Right? And you can see that like the probability will keep decreasing because you need all of these to be clear, and then you have to have an obstacle, right? So if you look at this like graphically, it looks something like this. If you want the shortest reading, you just need to have an obstacle there. The second shortest reading, you have to have no obstacle before it and then an obstacle. The third shortest reading, you have to have no obstacle in the 2 steps before it and then an obstacle. right? So you'll have like something that is like exponentially decreasing. Right? So don't worry too much about the math, but think about it as like, if I have an unexpected obstacle, the likelihood of a short reading is higher and it becomes like decreasing until the true distance, and then it's 0. And so the approximation you're going to do in your homework looks something like this. You're just going to do a linear approximation. As you go to a linear approximation until you start, you're going to see. Okay. The third is sensor failure. So it's saying that like, there was an obstacle, but I detected no obstacle. Right. And so it's going to be like, imagine I had an obstacle, it was supposed to return a LiDAR beam to me, but it just absorbed the LiDAR beam, or it sent it in some other direction, right? In that case, I will return a reading of C max, like the max possible distance, right? But it's actually not Z max. It's kind of like, imagine there was a LiDAR beam that is shot here. If I thought there was an obstacle, it should come back to me, but it like shot off that way, or like got absorbed by that material, right? In that case, my sensor is going to say that there was no obstacle, but there was actually an obstacle. And so you need to have some likelihood of getting these kind of failures, right? So in those cases, you're going to set the distance to distance max, like your max range of your sensor. And lastly, you have some degree of just random measurements, right? Like your sensor malfunctions, it returns random distances. You might have like weather, you might have rain kind of stuff in the environment, and so you have some just uniform likelihood between 0 to Z max of random measurements. Right? And so the way to kind of compute your LiDAR model is some combination of these 4 likelihoods, right? So you have, just to recap, we have the local measurement noise, which is a Gaussian around the true distance. We have the likelihood of an unexpected obstacle, which in our case is going to be this like decreasing linear function from 0 to the true distance. We're then going to have some likelihood of just having sensor failure, right? Something where you just like have the max distance. You're going to have some likelihood of random measurements, right? And so you're going to put them together, and your function is going to look like this weird combination of all 4 of them, right? So you can see that like, this is the local measurement noise, this is the sensor failure, this thing is like the uniform, and this thing is the unexpected obstacles, right? And so if I was not being probabilistic, like this would just be like like a point, like it's going to be like 100% likelihood to be around here, right? But because I'm modeling failures in my LiDAR, I'm going to consider these 4 types of failures: local measurement noise, unexpected obstacles, sensor failure, and then like random measurements, right? And that's going to give me my probability function. And the way you're going to do this in practice is you're going to have some weights that combine these 4 functions. And these weights are going to be these weights are going to be written by hand and tuned. A lot of your homework is going to be tuning these weights between these 4 coefficients. But there's no one size fits all there. It like depends on your particular environment, depends on your particular LiDAR. And you can't just like find one thing that fits on everything. Okay, I think we're at time, but just to kind of wrap this up, the way the LiDAR algorithm is going to work is you're going to take your many beam LiDAR, you're going to write it as the product of single beam LiDARs. And then you're going to say that you're going to use the robot's current state. So like the way that you're going to implement this in practice is you're going to have like a true map of the world, right? You're going to use, let's say you're trying to compute the sensor model for some XT, right? And the map, you're going to like put your robot in the map. You're going to take the like true obstacles. You're going to compute the true distance in different directions, right? That's the true distance ZTK star. And then you're going to add the like 4 source of noise we just talked about before, right? And so the way you're going to compute the ZTK star is you're going to put your robot in the true map, and you're just going to measure the distance to obstacles in different directions. Right? Okay. And so you're going to put your robot in a particular place. You're going to shoot LiDAR beams in different directions. You're going to measure the true distance. And then you're going to like add this noise that we just talked about, right? And that's going to give us our like measurement model. So remember with the measurement model, it's saying that like if this was the true state, I don't know the true state, but if this was the true state and this was the map, this is the likelihood I would get this measurement reading, right? And we're going to flip it with Bayesian filtering to give you the state. Okay, I think let's end here, and we will cover particle filters next time. So no class on Monday, but I'll see you guys on Wednesday. Thanks. Enjoy your long weekend.